Welcome back to the channel. In today's video, we are going to be testing pushrod rigidity and seeing how it affects engine performance. We all know if your pushrod isn't stiff enough, you can have bad valve train harmonics and the valve won't open fully as the cam pushes against the valve springs. However, is there a tipping over point if you put too heavy duty of a pushrod in for the combo and that extra mass and extra weight actually starts to harm your combo? So today I have the most popular 4 diameters and wall thickness pushrods available for most LS combos. We have a 5/16 80 wall pushrod that weighs 62 grams. We're also going to test the 5/16 105 wall pushrod, which is 70 grams. That's the pushrod I used to race this engine with. Then we're going to step up to a 3/8 80 wall, which is 76 grams. And then finally, I think this is going to be the tipping point. This 3/8 135 wall is 104 grams. What I think we're going to see is it'll make power with this rod. We might step it up and pick up a little power if this push rod is flexing. Maybe it's not. Maybe it's already good enough. But I think this is definitely going to show us a loss of valve train stability. So previously we made 708 horsepower with this engine on its break-in oil with the 5/16 105 wall pushrod. We have now swapped in some Valvoline VR1 10W30, and we're going to start over with the 5/16 80 wall, the lightest pushrod of the bunch. We'll get a base hit with those. We'll make a couple hits so we can average them together to have good data, and then we'll start stepping up pushrods and see how the engine responds. If you're new to the channel, we did a full build series on this engine, blueprinting, all the machining, all of the assembly, as well as a dyno video of how much power it made and the configuration I used to race it in, which was with the 5/16 105 wall. I forgot to mention in the intro, but this engine does have PAC 1209X valve springs. The way the camshaft is set up with the valve lift, we're going to be running about 170 on the seat and 520 open pressure. So this is a good combo to actually test that 5/16 80 wall pushrod. So I'm really curious to see how this test turns out. Right now we're doing a quick warm up on the engine, getting temperature on the motor, temperature back in the oil. And once we're fully warmed up, we'll start making our pulls.
ain't got no gas in it.
All right, guys, we are done testing all of the pushrod combinations. It's obviously a new day. We were here till about 9:30 last night working on the motor. And before I get into the data and show you guys the results, drop me a note in the comments below. Which pushrods do you think made the most horsepower? So with that, let's flip you guys onto the computer screen and we'll go over the horsepower charts. All right, so let's start with the 5/16 80 wall pushrod. And again, really quick, just for memory's sake, this motor has a PAC 1209X valve spring. And with the total valve lift that I'm running in this combination, we are approaching, or we are equaling 520 pounds of open pressure over the nose of the cam. And we are turning this motor up to 7,500 RPM, as you can see by this beautiful looking dyno graph. So this pushrod weighs 62 grams. It's the lightest pushrod of the bunch. It has the least what we would consider structural rigidity of the test subjects. However, it prints a really nice curve. 710 horsepower, pulls strong all the way to 7,500, no breakups. Everything looks really great. Now here's where things get interesting. Let me overlay the 5/16 105 wall dyno pool. Where is it? There it is. Now look at this. So the red curve was the 80 wall. The blue curve is that 105 wall. The 105 wall, it weighs 8 grams more than the 80 wall, coming in at 70 grams compared to 62. And we're gonna kind of just ignore stuff down here. I think we were pulling the motor a little too low, and the way the dyno was releasing it, we would get a little surge jump. What we're really gonna focus on is above 5,000 RPM from here to here, where the meat of the power actually is gonna be used. And on that 80 wall pushrod, we did 3 runs, and that was the best run. On the 105 wall pushrod, same deal. I did 3 runs. We made sure that the coolant temperature was the same. We made sure the oil temperature was the same. We made sure that the dyno correction factors were all the same, so we could have true, as well, I mean, the best data that we could possibly get with the tools available. And the charts don't lie. The heavier pushrod, while it is stiffer, lost power everywhere compared to the lighter pushrod. All right, so let me take the light 5/16 80 wall off this graph, just so it doesn't get too complicated. And now let's pull up the 3/8 80 wall. So the 5/16 105, which is now this curve, 70 grams. 3/8 80 wall, 76 grams. Let me open it up and look at that. They're basically overlaying, but you can see in 2 distinct key areas
basically from 6,000 RPM and above, the heavier pushrod, again, losing power everywhere compared to the lighter weight, thinner pushrod. And this was really interesting to me because I would have assumed that with 520 pounds of open pressure, with a heavy aftermarket roller tip steel rocker arm, long valves that are over 120 grams, that we would see the need for that heavy push rod to keep that valve spring and that valve train under control. But what we're finding is the lighter weight push rod, because I guess it had less inertia, it has less mass to get moving, it's easier to accelerate, is actually making more power. So here I overlaid the red curve as the 5/16 80 wall, and the blue curve is that 3/8 80 wall. And now we're seeing some serious horsepower. We're seeing about a 10 horsepower drop across the pool. Now here's where things get really interesting. And again, let me take off the 3/8 80 wall, and let me overlay you a 3/8 135 wall. This push rod is 104 grams. It is 42 grams heavier than the original 5/16 80 wall, almost 50% heavier. And look what it did. It brought the power back a little bit. Now it's still down. The 5/16 80 wall still made more power, definitely in this area and up top. But if we overlay the 3/8 135 and the 3/8 80, here's their curves. The 135 actually made more power. Red curve, 3/8 135 wall. Blue curve, 3/8 80 wall. A lighter weight push rod. However, the 135 picked up everywhere. And again, we did 3 pools. We made sure every correction factor. We made sure every temperature, every variable was repeatable and was constant. And you can see that I guess it just doesn't quite matter. So now let me overlay the heaviest and the lightest again. We have that 5/16 80 and that 3/8 135. And again, the 5/16 80 is coming out on top. Really interesting data. So now let's talk about what are our key takeaways from this experiment. What did we learn? What can we apply to our engines in the future? And I seriously think, guys, for a hydraulic roller, small block LS, or small block Chevy, small block Ford, a hydraulic roller engine with valve spring pressure below, well, even with valve spring pressure up to 520 pounds of open pressure, run the 5/16 80 wall. It's enough push rod. It's not deflecting. It made the most power of any push rod in this entire test. Something we didn't do was run a stock ball end push rod, mainly because the balls could pop off and could damage componentry. But maybe with a stock push rod, you might see that weakness shine through. But for any hydraulic roller, small block combo, put that 5/16 80 in there. It's plenty of push rod. You don't need the 105. You don't need 3/8 stuff. Keep it lightweight. Especially for, this LS engine with those PAC 1209X valve springs. It's pretty hardcore. I have to run that steel roller tip rocker arm. We're running a Johnson short travel axle oiling lifter for reliability's sake. Whereas most LS combinations, your typical heads cam build, your typical cam only build, you guys are running a 660 dual spring and about 620, 615 valve lift. With that valve lift and that spring pressure, you're only approaching maybe 420, 430, maybe 440 pounds of open pressure. This combo was having 520 pounds, and that 5/16 80 wall still made the most power. So if you're putting a combo together with a standard Brian Tooley, standard Texas Speed, 660 valve spring, you don't need a hardcore push rod. Put the 5/16 80 in. It's more than enough for what you're doing. Keep it lightweight. I think what this test really showed us is lightweight wins over rigidity in the valve train department, which is really interesting because in classic engine hot rodding, and if you buy Smokey Unick's hot rodding book and Grumpy Jenkins' book, and you talk to any old timer at any car show, they're going to tell you that on the push rod side of the valve train, make it as rigid and as stiff and as hardcore as possible, and on the other side of the valve train, on the other side of the rocker, that's where you need to keep it light. I think what this is starting to show us is if you can keep it light anywhere, it's better. It's going to respond better. The valve train's going to react better. And again, with this much spring pressure, we're not deflecting that push rod, causing harmonics. I think the heavier we start going, we actually start introducing harmonics into the equation. Now, if you're building a big block Chevy with a solid roller valve train and valve springs in the 700-pound range, obviously put a hardcore 3/8 pushrod in there. But again, you have to look at the application. That's why we get a ton of messages and we get a ton of questions about what do I need to run for this, or like what pushrod is best. You know, these types of just open-ended umbrella questions, and they're really impossible to answer because every application is slightly different. There is no best, you know, this is the ultimate lifter, or this is the ultimate pushrod, or this is the ultimate rocker arm. It doesn't quite exist anymore. It's all application dependent. So if you're planning an engine build and you want to find the last 2 horsepower like we did in this test, just talk to your engine builders, guys. Don't try to research this and try to engineer this all on your own, because your engine builders might have already done a whole bunch of testing their entire career trying to become experts and really dial in their combos. And so anyways, we're going to leave the 5/16 80 wall pushrods in the engine. They made the most power on the dyno. We saw no signs of valve train deflection or deviation. Now, we don't have a spintron, so we're not able to measure, you know, things, but all we have is the data in front of us, which are the dyno graphs. However, the motor is now about to go back onto the dyno. You actually might be able to see it right at the tip of my finger in the back corner. We're going to start our intake manifold test session today. So you guys will have to subscribe to my channel so that you can see that video when it comes out in a few days. Thank you guys so much for watching. Let me know in the comments below if there's anything else that you want to see tested, proven, any myths busted on the dyno. And I'll see you next time.